I'm Tariq Khan. I am Chief AI Officer and co-founder at Reteta. A brief about Reteta. Reteta is an automated scribing app that attaches to any EHR and listens to the patient-physician conversations and converts it into SOAP notes, and also provides you with medical codes in real time so that if any documentation changes are required, physician can change the documentation there and then by doing more conversations. So first of all, I'll talk about what did we want to achieve through our AI and choice of LLM. So the main problem in trusting LLM's output in clinical note-taking and coding is trust. And trust is required for your regulatory compliance. Trust is required for your user to buy into your AI and leave the traditional keyboard method of EHR operation. We were concerned about two components of trust, which is LLM models hallucinate and LLM's model give non-factual information. And almost everything that we'll talk today will be discussed in the light of this aspect of trust. So first of all, I'll give you a quick intro of how do we bring trust to LLM-based healthcare technology. So the first most popular approach for bringing trust is RAG, which is retrieval augmented generation. In RAG, what we do is we ask LLM to not share its own general knowledge with us, rather go to a database, which is a vector database, retrieve the most relevant documents from the vector database that can answer a certain question, and then read those documents and give us answer from those documents. So what happens is it reduces the chance of hallucination substantially. It also adds a lot of factuality, and it also gives you a chance to ask LLM, where did you come up, how did you come up with this information? So it can tell you document A, document B, page number 3, number 4. So that's why it's one of our favorite technique to inculcate trust in an LLM-based health technology. When is it recommended to use RAG? When you are up against a problem in which information changes very quickly and a model trained in 2 years ago or 1 year ago is not going to work, you need RAG so that your LLM can only use its linguistic power and not the information. The information should come from your documents. The second best use of RAG is when you need factual answers rather than opinions, or like you need facts rather than opinions, or you need numbers rather than procedures. So LLM does a very good job, and it's very easily you can very easily double check it. It's explainable because it will give you an answer, and then you can go and check the PDF from which it got the answer. An example of RAG-based solution could be when you want to update your customers, when you want to tell your customers in a customer service setting what is their recent account condition, or what is their recent payment plan, etc. So the information changes a lot in a customer database, and RAG can give you the most recent information. There are some cons to using RAG. So RAG uses vector database and it's using neural embeddings, which is a retrieval technique. Every document is passed through a neural net. That neural net assigns an index, which makes the document searchable. So if your neural indexing technique is not robust, or it is not with high recall or high accuracy, your LLM will not even find the information that it needs to read to answer your question. So that is a con, that it depends on the retrieval accuracy, and retrieval system has to be usually purchased separately as a private IP from some company. So it adds to the cost, or it adds to the technical implementation complexity. As RAG is doing two calls. One, it is extracting a PDF or a document, and then it is calling LLM to read that document. So those two call pipeline takes more time than a call to an LLM direct. So slow response is a problem, and a lot of LLM engineering needs to happen to make it, LLM ops and machine learning engineering needs to happen to make it faster. Data access management becomes a problem because you retrieve data from an encrypted system, a system that is HIPAA compliant, and then you put it in a vector DB for quick retrieval for knowledge extraction. And then if I'm not allowed to read a certain information, but in a vector database, I might be able to access it. To access management becomes a rabbit hole when you take all your information in a vector database and then extract those documents from there. So it needs additional engineering and cost to handle that. Compute, although it's not heavily GPU intensive, but still it requires separate compute for extraction. So you need to retrieve and extract the documents first, and then you need to call LLM. So there are, again, two models running in parallel. So there is some compute cost. The second approach is in-context learning. So if a model has good enough context length, you can teach the model there and then. So I'm showing an illustration of how to give in-context examples. So we are giving examples of statements of how to comment on a cuisine or a restaurant and how a comment would be positive or negative. And then we are asking the model, hey, there is one sentence, give me your opinion on whether it's positive or negative. So we taught it first, and then we asked the opinion. So we are not asking to do RAG, but we are teaching it in the prompt. So when you teach your model in the prompt, it is called in-context learning. The benefit of this method is quick task adaptation. So let's say you're working in a department, in a back office, in a hospital, and you have to solve multiple problems different time of a month. So you want a model that you can re-customize every week for a different hat that you're wearing that day. So quick task adaptation is the benefit. That's why you can quickly train it by giving 10, 15, 5 examples of what you want it to do, and then it will follow you. Then if you need highly structured output, like some people are okay with just an answer like a chatbot, but some people want XMLs or HTMLs or some other form that they can then ingest into APIs. So in that case, context learning or long context models with context learning help you a lot because you can give, let's say, 30, 40 examples of what type of XML or HTML do you want to spit as an output. Few short learning is, again, a benefit, because if you have a problem that like rare diseases or departments that don't have a lot of data about their patients, in that case, it allows few short learning. So it doesn't require you 50,000 of patient records. It can do with 5, 10, 15, and still it will do a very impressive job. So that's the benefit of in-context learning and the reason for choosing it. And the one con or one downside is that if you don't have enough data to provide to it while doing the learning, while giving the examples, then it would not perform. What it means is that anytime you want to repurpose an LLM in in-context learning, you need to work harder than simple prompting. You need to add more context to it. So you need to be ready for that extra effort of teaching the model. The compute is saved in the operation time because it's not fine-tuned. But initial models, the initial pre-training of the model is expensive. The models that have very long context are very expensive to train. So as long as somebody else has trained it and you're just subscribing to the model, the fine-tuning cost will be reduced because it's not fine-tuning, it's only doing in-context learning. And then the third method for trust and lack of hallucination is fine-tuning. So when you have a very domain-specific problem to solve and you're not happy with the performance of generic LLMs like Llama or GPT, so then what you do is you take the pre-trained model, you make another data set of, let's say, 20,000, 10,000, 50,000 patient records, and then fine-tune it. And after fine-tuning, the model is called fine-tuned model version of the actual model. So you can fine-tune when the problem that you're solving is not visible in the general data, like GPT doesn't know about that data or Llama doesn't know about that data. Then you have to come up with a data set and fine-tune your model, because you're going domain specific, highly domain specific. If the second usage scenario is if you're not confident with the performance of GPT or Llama on the task that you want it to do. One example is aspect-based summarization. So aspect-based summarization, one example is creating SOAP notes. SOAP notes has around 4 sections, sometimes more, but it has 4 sections, and each of the section needs to be added something. So the summary, SOAP note summarization is not loose-ended summary. It's a summary that needs aspects. It needs sections. So that is a specific task, and sometimes LLMs suffer in following you to compress all the information into those 4 boxes. So for that, then you need to create a data set that gives patient-physician conversation on one hand, which is raw data, and then the boxing into 4 sections of SOAP as an output. And you need to give like 10 or 20,000 examples, and then model will be fine-tuned on SOAP notes creation. That's what we do, by the way, in my company. So we give examples of physician-patient conversations, and as an output example, we give SOAP note created from those conversations. So the model learns how to take a raw, casual conversation and then put it into 4 boxes. Sometimes LLMs give you a very broad answer, which is not wrong, but it doesn't help anyone. So that non-relevant answers is a problem. And if you want the LLM to behave like an expert, then you need to do the fine-tuning. Fine-tuning is the most expensive out of these 3 techniques, because it's going to take thousands of data examples and then almost like train half of the model more. And once you fine-tune it, it's rarely useful for other tasks, because now it has become an expert. It has some GPU cost for retraining. Now I'll talk about more use case areas and where you need to fine-tune, where we can go without fine-tuning. So the first problem that I'm going to discuss is medical coding. In medical coding, let's say you want the model to consume SOAP notes and then create ICD-10 codes out of SOAP notes. There is a study by Exofer et al., and they suggest that if you take fine-tuned model like Clinical BERT, and you can see it in the green color on the top green color, it can do ICD-10 coding, but it doesn't perform the best. The best model they found out is your GINA embedding, which is on the top right corner, which means that if you have a generalized model, it doesn't fail in finding the ICD code for a patient-physician conversations. And then what was the reason? According to them, patient-physician conversations is a open conversation. It's an open discussion, and you can see so many variations for the same plan and same assessment. There are so many combinations of conversations. So if you take a fine-tuned model, the fine-tuned model doesn't have diversity and experience of tackling all those different scenarios that end with the same plan of a physician. So that's why they suggested that broader generalized models, non-fine-tuned models, perform very well in the coding problem. And of course, this gave us some narrowing down in our research while we were making our product, but we did not use exact same models. But the hint was enough to, reduce our research cost on how we implement our ICD-10 coding model or CPT coding model in Reteta. Diagnosis is another interesting area. Of course, regulations don't allow direct diagnosis, but you can use a diagnosis AI in physician assistant apps that help physician in remembering everything that they need to remember. So in diagnosis, we consulted this study so that we can have some guideline to save our research budget. What they did is they compared generalized models like MedPalm with specifically fine-tuned models on a hospital data. And they came up with the fact that MedPalm and Bioclinical BERT, all of them were not performing well because they chose the hospitals that had specific specialities, that had specific conditions, that has a specific patient demographics. And MedPalm is a global model. It doesn't know the specifics of one county or one hospital chain. So the final verdict was that fine-tuning improves the diagnosis power compared to the broader medical LLMs that are trained for the whole world. Medical summaries, again, I'm discussing this. One example is SOAP notes. So for SOAP notes, the conversations can go anywhere, and the generalized models hallucinate. And fine-tuned model like fine-tuned llama model performed best in this one study that I'm showing here. And we as a company also agree with the fact that if you fine-tune it, you tame down the hallucination probability, you tame down the non-factual information probability. Of course, you can't just rely on fine-tuning a model and then asking it to make SOAP notes. There is a lot that goes into it. For example, RAG goes into it. RAG with fine-tuning is our favorite approach at our company. And then there are so many other models required in the pipeline that do the guardrailing, that do the sanity checking to make a real product. But as a baseline, you need a fine-tuned model for summaries, any medical summaries. So there are like 10, 15 types of medical summaries that can use the same suggestion that I am giving for the SOAP notes creation. So in summary, if you're doing aspect-based summarization, any summarization in a medical setting, you should prefer fine-tuned models. And the best scenario would be that you fine-tune it on the specialization in the area in which you're going to do the summarization. For medical coding, generalized models don't miss out. They almost always retrieve the codes. And with RAG, you can also do the evidence mapping, which is, hey, tell me why are you assigning this code? And then diagnosis, which can be used in physician assistant apps. Fine-tuning can help, but if you're fine-tuning on a very data-rich, good hospital chain with a lot of digital transformation, it will perform very well. But if a hospital doesn't capture good data, or most of the people just type anything into EHR, then the data would be garbage and your fine-tuning would be worse than the generalized model like MedPalm. So that is all from my side. Whatever I learned in Reteta as a chief AI officer, I'm open to any questions if you have any. Yes, please.
Already tried in hospital for this kind of technology?
Yes.
Which hospital?
So let me answer a question. She's saying, did we try this technology in a hospital already? So we have multiple consultants that are working on research projects, WHO projects, and they are our consultants, and they want to use this technology in their own hospital in the research studies. So we have tried it in South Asia in a couple of hospitals. All right. Thank you all for coming.